Since none of you know where that is, this is a small R&D company located in the DC area at National Harbor. We have a Ferris wheel. And we're located in a little office in the back there. What we do. So we have over 13 years of experience moving research in AI and data science through the math, science, and engineering steps necessary to make the jump from theory to practice. We currently have 3 projects in data privacy. We're working with DARPA Brandeis. We're working with the US Census Bureau. And we're providing technical leadership for the NIST Differential Privacy Synthetic Data Challenge. So this is probably the only talk this workshop that has audience participation and worth $80,000. So yeah, feel free to tune out for the first 2 parts if you want to, but you should pay attention for the third. All right, so at Knexus, our priority is to develop the tools and technologies necessary to facilitate safe, successful public adoption of new research concepts. And we're going to be talking about our work with that. On the DARPA Brandeis project, we are working on noise-resistant decision metrics. And the application here is privatized analysis of the call text graph to alert emergency responders at crisis onset. This was a set of slides that had to go through 3 agencies. I'm not speaking for anyone. So this is what the system looks like here, a high level, what we're talking about. We have a crisis in a city. It originates at a city block. People call each other. This is going to show up in the CDR data. And this is plenty of social science research documenting this. What we have here is just plain old simple Laplacian noise call volume counts in the city blocks. And the question is, can we from this determine which block the crisis originated in, maybe information about the severity of the crisis? We started out our work building a social network generator, because what we wanted to do was build crisis detection that works. You can be 80% you can be 80% correct if what you are trying to do is release a number. But if what you're trying to do is release a decision, you're either 100% correct or you're 100% wrong. And if you're only right 80% of the time, that means one out of 5 times you're calling wolf. So it's not really something that you can afford to do. So we started out by building a data synthesizer that would let us test how well our metrics worked over lots of different data situations. We built the system that you just saw, web application. And then we started in on our crisis detection metrics and evaluating how well they did. Quick little bit of theory here. So if I'm looking at communications data, I'm looking at social network data, whether I have the social network or not. That's what's going on. Obviously, differential privacy over social networks is an interesting game. We're not doing node privacy or edge privacy. We're doing contributor privacy, which offers privacy at the level of 1 row of the adjacency matrix. All right. So let's try this. I want to detect a crisis. What should I do? Something bad happens. There's a shooting, an attack. People freak out. They start calling. I'm going to see a spike in call volume. Nice simple analysis, sensitivity of 1. What is the spike due to the crisis or the noise? So here is how we are computing error. Everybody likes to say mean squared error. This is what we mean for us. Here's the ground truth. The crisis is actually here. Here's an example of a series of things we could get wrong. We could think that there was another crisis over there, a false alarm. We could put a warning in a place where there's not a crisis. We could also fail to detect the actual crisis. And so for our mean squared error here, we're counting up all the mistakes we made in each iteration. And you think, okay, maybe this is sort of okay. If I look at this from epsilon, 0.1, it's kind of got that nice flat curve. But again, we really can't afford mistakes. And if I make this, if I tell you how many mistakes we're making here, it's a fair amount. We need to do better. So we'll try and do better. And this is where, in order to do better, we actually have to understand the behavior, the social science of what's going on in our data. So it turns out in an actual crisis, people call out, and then their friends call back in to check on them. There's a second spike. And that's shown up in all of the literature on this. It's very well understood. So we're like, okay, let's try detecting the second spike. Well, so first we're going to look for the first spike and then the second spike. And that gets us a little bit more accuracy. If we insist on seeing 2 spikes, we do a little bit better, but honestly not that much better. So we need to understand even more what's going on with the people and what's going on with the data. This one also doesn't work, and I have a lot to get through, so there we go. But now we start to get to one that does. So how do I know that the people are calling out because of a crisis versus they're calling out because of a football game or something other random? Well, it turns out the weight of the information I'm communicating changes the impact it has. If I'm calling out due to a crisis, you receive that call, then you start calling people that you know, spread the information further. And so the initial social science analyses to determine the spread of this further information are not things we can easily privatize. They involve tracking down things to specific individuals, but we can, on aggregate, and again, sensitivity 1, all we're doing is partitions of call volumes here. But we can, in aggregate, look at how the call volume from the crisis block changes the outgoing call volume of the blocks that are receiving most of the calls from the crisis block. And that works quite well. So there we go. Now we're starting to get into something useful. And there were interesting social science, math, and engineering problems that needed to be solved, understanding people's behavior, in order to get us down to a point where we had, at a nice epsilon of 0.5, no false detections. And that's starting to get down to practicality. So that's my takeaway there for this third, which is that it pays to understand the data. And especially, it pays to understand social behavior and to try and capture those patterns sort of as closely, as efficiently as we can with privatized metrics. Neat. Okay, Sensen. Now for something entirely different. Okay. So myself, Mike Heineck, Jason Swage, Christine Heiss, Karan Bhagat, Joe Grouse, Conrad Rauscher, Jeffrey Hodges, and Jonathan Woodell at Knexus are working on the Sensen project, where we're providing research engineering software development effort for ongoing census privacy efforts. We're developing effective, usable software systems that address the problem of data privacy. So there's a few people from the census here, and I did not know what all they'd be talking about, so I picked something that they probably wouldn't be talking about. We're going to look at our evaluation suite. I think this was mentioned yesterday in the panel, the question of how do we tell if we have good data? And that is an open and fascinating problem. And so our evaluation suite is designed to address it, and it's applicable to synthetic data research in general, even though it was developed for the the non-differentially private synthetic data for the 2019 ACS. Okay. So I'm going to take a moment and do something boring, but you should all pay attention anyways. And I'm going to go through the definition of synthetic data. And that's partly because this video is going to be archived and I want this to be available for other people. But it's partly because maybe we should pay attention to it. So given a data set D fitting the schema S, a synthetic replacement for D refers to an artificially generated data set that fits the same schema and is distributionally similar. You want overlap on individual rows between the two data sets, should be purely coincidental, and it should happen sort of reasonably low probability. There's a lot of different ways for producing it. In general, it's usually produced by capturing the distribution of the data in some fashion, and then sampling another data set from that same distribution. High-quality synthetic survey data should ideally be as similar to the original data as two uniform random partitions of the original data are to each other. If I'm producing a synthetic data set and I can tell the data users that it's no farther off from the real data than sampling error, then essentially if I had reached my hand into another universe full of completely different people, but living in more or less exactly the same circumstances, that's when it becomes something that's comfortable to use. Privacy-preserving data generators can be iteratively tested and improved safely using previously released public data sets of the target schema where available. So helpful for ACS, so you're looking at the 1940 census data. Okay, so the obvious question. How closely are we all paying attention?
Where is this definition taken from?
Me. Feel free to argue if you like, but this is how I understand synthetic data. So the obvious question is similar how? Right? Synthetic data should be similar, but what do we mean? So that's what we're looking at. Always good to have a first check, right? First take at the problem. Makes sense to look at individual variables of interest to verify that their values are distributed similarly between the two data sets, so basically histograms, basically tables. So the census has a wide variety of tables. And our table-based evaluator, and I should say evaluator suite. I'm going to show a variety of ways that you could evaluate synthetic data. Evaluator suite. Here we have a synthesizer with the, so this is a multiple imputation-based synthesizer. And this is with one variable ordering, and this is with a different one. This variable ordering is better. And here we have the cells where there is significant variance between the real data and the synthetic data are highlighted. And it's because of evaluations like this that we know that variable ordering can have an impact. And that is one of the math and engineering problems that we're investigating.
Sorry, what is a variable ordering and where?
Okay, multiple imputation-based synthesis. So the idea is, given a data set with a series of features, you're essentially modeling the data set with those features in order. So you model the third feature based on the values for the first two. You model the fourth feature based on the values for the first three, and so on. And the better, potentially, you might assume, that the better the earlier variables predict the later ones. So the more the independent variables are earlier in the ordering, you do better. But maybe not. We're not sure. What we know is that variable ordering has an impact, and so we're looking into it. Okay, so that's just tables, though. That's maybe 2 or 3 correlations. But let's look at correlations more deeply. So as part of the NIST Differential Privacy Synthetic Data Challenge, which we will be getting to later, there we had a problem where we needed to efficiently snapshot how good the synthetic data we were getting was. One of the first methods we came up with that we used in match 1 was a 3-marginal-based metric. So using different we here. That was actually created by Dr. Sergey Pogodin, who is basically a tech lead for Topcoder, what they call a co-pilot. And so 3 marginals turned out to be very flexible. And this was a randomized sample of 3 marginals, computed very nicely, caught some good patterns.
Samplings of the variables, right?
Samplings of the variables, yes. Yeah, we did not do all K-choose 3 possible 3 marginals. It's a random sampling, such that every variable ends up in at least 1 3 marginal. Okay, so this was published on the NIST site. You can all go to the challenge site and read the details of how this metric is computed. It gives a nice number between 0 and 2. After it was published, we saw the use of that over on the SynSyn project and added this to our evaluation suite as a K-marginal. We will compute all in choose K possible marginals for you there. It may take a while. We allow, customized bucketing. We do data subselection filtering. We give more detailed reports on where variations occur, if they are there, and we basically let you use that to inspect where your synthetic data is starting to deviate from your real data. Third up, though, that's still, in some sense, sort of randomized heuristic. Let's look at something more holistic. Dr. Claire Bowen, so she did her dissertation on differentially private synthetic data at the University of Notre Dame, possibly dumb, developed a technique called the SPECS method. And so this is synthetic data generation, propensity score matching, empirical CDF comparison based on Kolmogorov-Smirnov. And it looks like that. It is what it says it is. And basically, what that gets us is a graph like this. So this is using her suggested approach with the logistic regression. And this is a tuned synthesizer where you only see one line. That's because they're actually performing so well, the logistic regression can't distinguish the two data sets. So basically, your approach here is you're training a classifier to distinguish between the real and the synthetic data, and then that gets computed down into one nice single number that you can use. This is a well-tuned synthesizer. This is a very poorly tuned synthesizer. You can see the difference. Okay, so at Knexus, we have our own, not quite an evaluation suite yet. It's a prototype, but it works pretty well. One thing it lets us do is it lets us substitute other classifiers in. And so here we can see that using multi-layer perceptron network actually gets us more distinguishing power, more discriminative power than we did over in the logistic regression. So now we can see we haven't done a perfect job. Now, are those differences problematic? It's a good question, right? We know they exist. Maybe they're fine. Yeah.
Quick question. What are the plots on the right-hand side?
That is, the plots on the right. Sorry. So well-tuned synthesizer, poorly tuned synthesizer. Okay. Good performance, bad performance. Yes.
Is this plotting two ROC curves of a classifier run on one data set and the other on the true data set versus a noisy data set, and then comparing the AUCs between them? Seems like...
Yeah, so this is just the, it's the CDF of the propensity score of the classifier.
Right.
Okay.
Something like a false positive rate with a true positive rate where you cut off by a threshold on the score of the relative regression.
This is a fascinating conversation I would love to take offline. But part of this is like I said, this is what she's done in her work, and I won't speak for her either, but I'd be happy to talk to you about it. And her dissertation is fascinating. Yeah.
But if you consider it some sort of a baseline, taking the data and partitioning it into two, you should be, I don't know what is the PS score or whatever, but any reasonable score should have like some deviation of 1 over square root of n between them.
Absolutely. And yeah, we don't have a baseline here. In this particular two diagrams I've given you. That does not have, so sorry, yes, we do expect there to be some deviation. There is a question of whether the deviation that we're seeing here is a significant or problematic deviation. And that was me leading up to my next slide. So, okay. So in general, though, right, it's easy for us to just immediately talk about sort of open problems, things to think about here, right? Evaluation for synthetic data is a topic of challenging, active, and vitally important research. And we are not providing any canonical answers today. But the evaluation suite is designed to support that research. And things that we will be adding to it include the analytics package. And so the idea here is a set of analytics that look at things from the social science data user's perspective. And this is, again, to determine if we're starting to see two data sets that diverge. Are they diverging in a way that's problematic? We have some PCA techniques we have looked at, which gives us a nice visual representation. And then there are other NIST challenge heuristics that we intend to add to the suite as they come available. Okay. Any questions before we move on?
So you're using the Kolmogorov, I mean, is that for categorical? I mean, what, have you considered like Kullback-Leibniz or, you know, other sort of distance metrics between distributions?
So the KS is getting applied literally just to look at the distance between these two lines here. But again, let me make this bit clear. There are certainly more things we can do. And anybody who wants to talk to me about things that we can do, I will be happy. I will take notes. I will exchange emails. Absolutely. Okay. Are we good to get on to the $80,000 part of the talk? All right. The NIST Differential Privacy Synthetic Data Challenge. Okay, so this is an initiative by the NIST Public Safety Communications Research Division, and the two leads on the project. Mary Theophanos is the PI, and Therese Manley is the prize manager with PSCR. I'm providing differential privacy expertise and technical leadership. Topcoder is the challenge platform. They're doing implementation and also project management. HeroX was the challenge platform for phase 1, and Kyla still very much helpful for project management. This is the first national challenge in differential privacy. And we expect developments coming out of this competition to drive major advances in practical applications, especially for contexts such as public safety. The winners from Match 2 will be announced tomorrow, actually. Do I have any competitors in this room who feel comfortable raising their hands? Got a few? Awesome. All right, so very soon, guys. Match 3 begins next week on Sunday, and registration is open now. And we'll tell you more about how that works as we go. So let me tell you just a little bit about the Public Safety Communications Research Division, PSCR. So they are, their purpose is to drive research that can possibly help Americans' first responders. This is actually very important data analysis and privacy concerns because most fire departments don't employ data analysts. But obviously being able to understand if your fire department is providing adequate service to your city is a data analysis problem. But it's a data analysis problem with significant privacy implications. And so they are hoping that by funding this challenge, they're going to drive research that will allow safety departments to leverage the power of crowdsourced analysis to understand and improve their systems. Challenge also has advantages for us. So challenges provide researchers with a visible, open, and accessible shared pathway from theory to practice. They grab attention, they educate the public and potential investors about new technological possibilities, inviting the audience to follow along in the excitement as those possibilities are fulfilled, and this is already happening. People with Topcoder have been going to, and people with PSCR have been going to the big data conferences, and there was a lot of excitement. And this is why challenges often precede significant acceleration in the development of commercial products for new tech, as we have all seen happen with Kaggle, obviously with the DARPA Urban Challenge and so on. So what is the challenge, in case anybody doesn't know? So it began in the summer of 2018 with the concept building phase. We had white papers, and those were evaluated and put up for public judging. And we got, this is all on the HeroX platform. We got prizes out of that. And then we moved on to the second phase, which started this fall. And this is a sequence of empirical matches where participants implemented their systems and competed to produce high-quality synthetic data from real data sets. It is the first national challenge in differential privacy. I like saying that. I've said that like 3 times. But it's already not the last. So Topcoder has already launched a second one. I'm not involved with that, and I'm not sure who is. Potentially someone is. But this is why we think that as the data challenge format is a well-established archetype, and people in data science are interested in this, and we may see more data science-based differential privacy challenges. Those require some non-trivial adaptations to actually work. And we think those are questions that are important for the community to address. So what you're going to see here is a series of questions and complications that we ran into and how we resolved them and our reasoning. But we don't think these are the only possible solutions. This was our first shot in it. So we're very much interested in what you guys think and so on. All right. So Let's talk about the challenge. Things that we had to figure out in order to do the challenge. We wanted to, right? For the contest procedure, we needed to create a shared competitive benchmarking process for differentially private synthetic data generators. And there was a constraint, which is we haven't really had one of those before. If we did this as a one and done, we would have problems because the contestants are learning about the behavior of their solutions on our scoring metrics and in this context at the same time we are. So what we needed was for the contest to support teams iteratively evaluating, exploring, and then refining and resubmitting their solutions. So we wanted to support not just a chance to have a great contest, look nice, and hand out prizes, but actually support the evaluation and refinement process, the development process. So the way we're doing this, and this is actually sort of a common problem in data science contests in general, is with the top coder marathon match, which is a great form. So we're doing 3 marathon matches of increasing difficulty. Each match has 5 weeks of provisional leaderboard scoring. And the way that works is you just submit us a synthetic data set, you get a score on the leaderboard. You next day, you want to try again, maybe you submit and get a better score. This is followed by 3 weeks of rigorous sequestered evaluation. So at the end of the provisional leaderboard phase, we have everybody submit their everybody above a certain point level. We'll get into this. We invite them to submit their source code and their executable systems, and we do a very robust evaluation. And it's that robust evaluation that determines the prizes. A question that came up. To support iterative refinement without violating differential privacy, we assume that the data set that we give you during the provisional phase is public. So this is, again, sort of the ACS, or there's many other sorts of data sets out there that have been releasing anonymized public data sets for years. So you already have information about the data. And basically, our imaginary use case here is that a group like that wants to switch to using differentially private synthetic data. And so you have all of that, all of those years of public data available to you to refine your algorithm and your understanding. And then you just have to get the differential privacy right on that last private data set. And so the deal here, for anybody who might be interested in competing, is that the provisional data is public. You can use it however you want to. You can hard code things from the provisional data into your system. The sequestered data is different years or areas, different individuals, and different distributions, and possibly a different schema. And so please don't hard code too much. Okay. Yeah.
Maybe you're going to get to this, but what is the sequestered evaluation evaluating?
Right. So we will get it. There's a slide titled scoring. Yep. It is the same scoring that's used on the leaderboard. What we do is area under the curve, and as many epsilons as necessary to be able to confidently rank the solutions. I have a 10. I hope that came up recently. All right, we're going to move quickly. So differential privacy validation. So obviously the thing everybody's worried about. Easiest way to get a high score for synthetic data is just give us back the data set we gave you. Violate differential privacy. And it's also very easy to do accidentally, and it's very easy to do subtly and accidentally. It would be great to have automated DP verification, but we did not have, at least we have not had so far, the time and manpower to do an implementation of one of those systems. Came out more or less in the midst of our setting up the whole contest. So what we use instead is a SME review panel. I have every confidence in them. They have found a number of very subtle mistakes, mistakes that took me quite a while to figure out how to explain to the person who made them. Subtle mistakes. But we have to be conscientious of their time. And so what we actually have is a 2-step process. During the provisional phase, every Monday we have a telcon. We do a quick skim on all of the clear, complete privacy proofs that have been submitted. You submit your privacy proof, you submit your algorithm write-up, and you get 1,000 times point boost on the leaderboard. You fly to the top of the leaderboard. On the sequestered phase, invited contestants submit code. code guide and documentation, and an updated privacy algorithm specification and privacy proof. And this is when we pick through everything through a fine-tooth comb. It is very common for us to find things that are problems in the sequestered phase that we missed when we first gave you the pre-screening and the provisional phase. Okay, so data and scoring. Data should be relevant to PSCR's applications. We had to go looking for a good data set that got at their needs. What we used for match 1 was the San Francisco fire event data. So here's this thing. Topcoder has a policy, and it's very fair, that I can't tell any of you anything directly that we don't post online for all the possible contestants to see at the same time. So you can't have a special advantage. So there's a black box on match 3 at the moment. But we'll see about that. All right, so on scoring. We talked a little bit about this before. So the provisional scoring is done on the synthetic data sets. You just submit us 3 data sets at 3 values of epsilon. We score them. The score goes up on the leaderboard. Sequestered final scoring is area under the curve. And repeated trials, yeah.
At least the schema of the data, the same as the one for the...
It is...
Given or not?
Yeah, so it is very similar and it is given. Columns may switch order. So
Single table.
it's a single table, yes. So the schema between the provisional and the sequestered is maintained, except for columns may switch order. There are values. Please don't hard code to the values that actually exist in the data set that we give you, but rather to the set of possible values in the schema.
And the sequestered data, this is real data. It's not that you're trying to modify.
Oh, yes. No, it is always real data sets.
You're not deliberately changing distribution. It could or may not be.
Exactly.
Is it? I guess the question is...
It is real data.
Is it?
Sorry, it is real data. We are not messing with it. How similar is it?
But how similar is it? Because, again, or you cannot tell that.
I can't tell that, no.
But I guess over the years, let's say 2018 and 2017, are they similar?
It is true that 2018 is true, similar to 2017, and what I highly recommend doing is looking at the winner's announcement when we post that tomorrow on match 2. And it gives analysis of the sequestered evaluation for match 2, and that'll tell you a little bit more about things.
And eventually, will
sense?
you publish the data?
The data's, all of the data is already publicly available. You just don't know which one.
The sequestered one. Will you eventually publish the sequestered data?
It's actually already publicly available. You just didn't know which year we were using. All right. So how am I doing on time?
3 minutes and then questions?
Okay, well, we're maybe going into questions a little bit. Okay, so in match 1, we used a randomized, normalized, 3 marginal-based distance metric. In match 2, we used a row similarity metric. So the idea was pick a random row from the real data and look at this pool of rows that are similar to that row in the real data, see if that same pool is of a similar size in the synthetic data. So essentially looking at full row based distributional similarity, and I would be happy to explain that in more detail at any point. And we have another black box. Okay. This is an important one. So NIST is part of the U.S. Department of Commerce, and they provide guidance that helps U.S. corporations address technical needs. As a vital outcome of this contest, we would like to have stable, usable, well-engineered, and ideally open-source software solutions that can be further evaluated by NIST experts, contributing toward NIST's efforts to offer official guidance on DP synthetic data. So we were hoping to move people towards, from academic prototypes, maybe shaky ones, to very usable ones. But we understood that people may be coming in with just academic prototypes that were used to produce papers. And so the very first thing you have to do if you want to compete, just give us a data set. Use whatever code you have, get us a correctly formatted synthetic data set. If you come to the sequestered round, then we need a standardized input. Right? We're going to give it the delta and epsilon value. You can't hard code the schema. We'll give you the schema. It will be very similar, but there may be differences in column names and so on. And thorough code documentation that's aligned with your algorithm documentation. This is reviewed by multiple subject matter experts. The things are run by the tech leads. If we encounter problems, you're informed and you may get to resubmit. And so you leave, if you get a prize, you leave with money, but everybody who comes to the sequestered batch leaves with an externally evaluated code base. They'll be more easily shared, tested, and used by other researchers, potentially forming a stable basis for further production-level software solutions. So this is my offer. Participate in the contest, and we'll provide a free 2-month boot camp for your DP synthetic data solution. All you got to do on Sunday, or any time over the next 5 weeks, is sign up on Topcoder, send us 3 data sets at 3 values of epsilon, and we will walk you through the process of having a system that other people can use, that is well documented, that is easy to understand. All right. So here I'm going to do the thing. My contestants, do you get email notifications on your phone?
Yes, but we didn't submit to the match.
Oh, you're fine. Yeah. This is not the winner's announcement. So this is when I press post.
Wow.
And there we go. Now everybody online knows. So you guys get to know. There we go. All right. So we're going to be using the 1940 census persons level data for Colorado, which is where PSCR is based, as our provisional data. For our sequestered phase data, it will not be Colorado. All right. For scoring, to catch long tails, we are going to be using income inequality-based metrics. So both of the things we had done previously in the matches were bucketed. We will not be bucketing this match. And to catch degradation of accuracy over differences of differences, we're going to be doing pay gap-based metrics, which in 1940 are going to survive synthetic data. Okay, final outcomes. So $62,000 in prizes, and then if I do my math right, that's 5 times 4,000 for people who open source. That gets me the 80,000, 82. We would very much like to see open source solutions coming out of this. There will be further NIST research as a metrology lab to identify and establish metrics and methods for evaluating synthetic data. So there are 2 open problems here. One is generating the data, but the other, very much in NIST's wheelhouse, is measuring the data. And also, we would like to disseminate the lessons learned and the approaches taken through journal special issues, potentially, conferences, workshops, talks, and challenge participants will be invited to contribute. So I would very much like to see many more teams join us for Match 3. And more information on this will be forthcoming. And there you go. That's how to find us. Any questions? Any incredibly quick questions?
5 minutes for questions.
Can I just clarify?
Sure.
The code that people submit and win or don't win.
Yes.
They could be open or they could be closed.
They can be open or closed. It's entirely voluntary.
And you expect most of them to be open?
I would very much. We are offering $4,000 for the top 5 winners to open source their solutions. People do have the rights to hang on to their IP. So it is only we invite you to open source. Yes?
So I'd love to know more about the way you're doing the scoring, like measuring the accuracy.
Yes.
Is there like a document that...
Yes. So what there is, hold on, 2 seconds here. If you Google the contest, as it was suggested, you will find links to the problem statement. And this is on the Topcoder website. And that you will actually find not just a detailed description of the scoring, but also code. You can just run the code and do it yourself.
I mean,
So you're looking at...
Finding like this